I want to talk about very briefly how you find the area under the curve of a velocity versus time graph. Let's say I have this velocity versus time graph, and here is 1 meters per second, 2 meters per second, 3, 4, and 5. And maybe this is 1, 2, 3. These go up by 1, 4, 5. Okay. So it's fairly easy to see what the area is. Here's this area. This is under the curve. And even though we say under the curve, this is the area of the second part of this motion. So this object is moving with a constant velocity forward and then immediately turns around and has a constant velocity backwards. And so remember, the area is the displacement. Displacement is delta x. And so we find this area, we find the displacement. And so to find the area of a square, you just take the length of 3 seconds times the height of 2 meters per second, and that gives us 6. This is in the numerator, this is the denominator, these two cancel, so 6 meters is going to be our displacement here. And then here, if this is 1, I get 1, 2, 3, 4 seconds. And this is 1 meter per second, so the bottom has an area of 4 meters. If it's below the x-axis, negative velocities give you negative displacement. And so to find the total displacement for the whole trip, we just add both of these numbers together, and we get 2 meters is our total displacement. Now, this is easy to do if you have squares, but if you have an irregularly shaped something or another, it gets a little bit more difficult to see exactly how to break that up into squares or triangles. So let's say I have something that looks like this. Maybe it's here, and then down here. Let's not worry about negative things right now. Okay, so you have this weirdly shaped object, weirdly shaped velocity versus time graph. This object is speeding up in the positive direction or accelerating in the positive direction, has a constant speed, and then slows down to a velocity of 0. This whole time, this object has a positive velocity, meaning it's moving in the positive direction. All right. So when things get a little bit complicated and you're not quite sure how to break this up, I could see that there's a triangle here and maybe a rectangle here and one here and one here. You could do that. You could find those areas, or you can just start counting the squares. So when I count the squares, maybe I should have made this a little bit smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9. This isn't a whole square. This is not a whole square, but maybe this piece, 9, and this little piece count as 1 square. Maybe this piece here and this piece here count as 1 square. And so you sort of are estimating a little bit what makes a whole square, and you'll count all of those up. I'm going to pause and then I'll get back to you. Okay, so when I added all of these up, when I counted all of my squares, I get something about 55. Now, 55 squares. This is the thing that we need to make sure that you pay attention to is I counted up all of these squares, but 1 square does not equal 1 meter, because this square here is only a half of a meter per second by 1 second. And so 1 square, if 1 square is only a half, 1 square equals 1/2 of a meter per second, or 1/2 of a meter, I mean, then you have to multiply this by whatever the area of 1 square. So 1 square, you get 1/2 of a meter per square. And then you can do the math here, and what we get, 27.5 or something like that meters is our displacement. You'll see this most oftentimes in the case where it would go up not by smaller numbers, but maybe it goes up by 5. This is going to be fast, so 5, 10, 15. And if this goes up by 2s, 2, 4, 6, then each square would be 5 times 2, or 10 meters equals 1 square. And so you would have to multiply the number of squares by 10.